Swayam Prabha. Digital India. Educated India.
Right, now we begin our concluding session on naphthalene. This is where we have got so far. We have got the energy level diagram and we know what kind of energy is associated with what kind of symmetry. What we do not know so far is what are the actual molecular orbitals. We have only been able to generate parts of them, but we have not been able to generate molecular orbitals. So, now before going any further, before going to spectroscopy, let us try and generate the molecular orbitals of naphthalene knowing the SLCs. So, let us start with AU. For AU, we have two cells, right. It is something like half into phi I minus phi j plus phi k minus phi L kind of combination, both of them. Now, our task in hand is to generate a linear combination of psi 1 and psi 2, so that we get the MO. Please note that this MO is going to consist of 4 p orbitals. Phi 9 and phi 10 do not participate here, because there is no AU in phi 9 and phi 10. Later on, we will encounter a situation where phi 9 and phi 10 will also be contributing to the linear combination. So, if you have studied in organic chemistry, if you have seen these diagrams of pi molecular systems, you might have seen that sometimes on some of the atoms there is a dot, right. There is a dot, even in benzene it is there. What is the meaning of the dot? The meaning of the dot is that that particular atom does not contribute to a molecular orbital of that symmetry. Okay. This is our task at hand. We want to know what is this psi MO that we can generate by taking an appropriate linear combination of psi 1 and psi 2. What will be the symmetry of this psi MO? If I work with this psi 1 and this psi 2, A is not enough, AU, okay, you said U, but I did not hear it. So, AU, C1 and C2. Of course, you can understand that you can have different combinations of C1 and C2. One is going to be plus, one is going to be minus, and magnitudes can change. So, what you can do is, once again you can set up secular equations for these, exactly the same as what we discussed in the beginning of this discussion of naphthalene. You set up the equations, this is what you get. C1 multiplied by alpha minus C plus C2 into beta. Of course, I have jumped a lot of steps here. I have shown you only the final answer. I encourage you to work out these steps by yourselves. If you do not understand, please come to me, we will try to work out together. So, C1 multiplied by alpha minus C plus C2 multiplied by beta equal to 0, and the other one is C1 multiplied by beta plus C2 multiplied by alpha minus beta minus E, that is equal to 0. Two equations. What are the unknowns here? C1 and C2, because we know what alpha is, we know what beta is. Do we know what E is? We even know what E is, isn't it? Remember? We are talking about AU. So, E has to be minus 1.618 or 0.618. Only two possibilities are there. So, what you do is, first of all, you take 0.618 and substitute, you are going to get, okay, one more condition is C1 square plus C2 square equal to 1, that I think is well known. So, you have two equations, one is C1 plus C2 is equal to 1 by E, which is also equal to 1 plus E, is equal to 1.618. The other one is C1 square plus C2 square equal to 1. Substitute, you get C1 equal to 0.85 and C2 equal to 0.526. Okay. So, this is the plus combination. If you want the other one, what you do is you take this minus 1.618 and see this is all consistent, right, because if you remember E equal to 0.618, that is for a bonding MO, because it is multiplied by beta, beta is negative. E equal to minus 1.618, that is the energy of an anti-bonding MO, because it is multiplied by beta, beta is negative. So, what we have got is we have got C1 and C2 combinations, both are positive, and now we are able to write the MO. The bonding MO with AU symmetry turns out to be what you see in front of you. All right, we have been able to generate the MO. Good. So, is that good or is that good? We have been able to write the MO now. So, Jalodha, finally you are answered, right. We started with, so the whole idea of using symmetry is to simplify problems in quantum mechanics. We try and break up big problems into smaller parts, but then we cannot afford to forget to combine them also, right. That is what we are doing now. So, you can do this for each and every symmetry of all the orbitals. If you have time and energy, you can do it. This is the answer. Which orbital have we worked out already? This one. Okay. And where is its partner? Where is the other AU orbital? Here, right. Remember, E is minus 1.618, that turns out to be 0.263 multiplied by the first SALC minus 0.425 multiplied by the other SALC. So, you see there is a minus here. Okay. And can you identify the bonding MOs? Can you identify the energies of the bonding MOs here? The top 5, right. In fact, the highlighted one is the highest occupied molecular orbital. Okay. So, what have we obtained so far? We have obtained the expressions as well as energies of the MOs. Okay. So far so good. This is your energy level diagram, you know what these are like. Now, of course, just energy level diagram is not enough, we want to get into spectroscopy, because well, again there is a cliche I say everywhere, experimental results are the only truth, right, just theory is not enough. So, where is my experimental result? What is the experiment that I do to see whether my quantum chemical calculation makes any sense or not? The experiment is spectroscopy, right. As one of our illustrious colleagues had once said, spectroscopy is quantum mechanics in action. So, but then we have to arrive at spectroscopy from here as well. To do that, first of all, what we do is we talk about symmetries of states, which has been discussed earlier. Let us see if we can determine the symmetries of the ground state and the first few excited states. What is the ground state? Look at this configuration. You have these 5 bonding molecular orbitals, all of which are completely filled. So, what is the, how do you name the state if all occupied orbitals are doubly occupied? First of all, singlet, triplet, doublet, what is it? Singlet. And what is the name of the state? It is a totally symmetric state, right. You basically take a product of everything, it will come out to be totally symmetric. So, ground state in this case is predictably singlet A1G. I have not written the singlet here, but it is singlet A1G. Okay. Give me a sec. I think I have gotten a little carried away here and I have written an incorrect name. It is not A1G. There is no 1, isn't it? It is just AG. A1G is there in benzene. So, what I have written A1G, that is a mistake, that is a hangover of benzene, right. So, AG, you can please correct it, it is AG, singlet AG, fine. Now, let us go to the next one. This is one excited state that I can think of. How have I formed it? By a HOMO-LUMO transition. HOMO to LUMO transition is the lowest energy transition. This is what it is. So, what is the electron configuration now? It is B1U2, B1G2, B3G2, B1U2, A1U and B2G. So, all the doubly occupied orbitals do not matter anyway, right. What matters is AU and B2G. So, AU cross B2G, what will I get? Direct product of AU and B2G. Well, you can work it out looking at the character table or product table, or you can remember direct product of A and B is always B, direct product of G and U is always U. So, what you get is B2U. And remember, we write states, symmetries of states in capital letters, we write symmetries of orbitals or wave functions in small letters. Okay. So, this is your excited state obtained by HOMO to LUMO transition. Next, okay, well, let us finish this. What is the energy? This one is 0.618 HOMO and LUMO is minus 0.618. What is the energy gap? 1.232. So, that transition should have energy of 1.232. What kind of transition is it? AG, singlet AG to singlet B2U transition. Okay. Now, next let us think of another one. Let us say I have performed a HOMO to LUMO plus 1 transition, that will have higher energy. What is the energy difference now? 1.618, is that right? 1.618, this is minus 1 and this is 0.618, minus 1 minus 0.618 is minus 1.618 multiplied by beta, beta is actually minus 1 in our convention, that becomes 1.618. Now, see what is the electron configuration now? AU B3G, only the orbitals that are singly occupied matter. AU B3G, what will be the direct product of AU and B3G? B3U. So, this is a B3U configuration and the energy is 1.618. Let me try another kind of excitation now. What have I done so far? I have done HOMO to LUMO, I have done HOMO to LUMO plus 1. Now, let me try HOMO minus 1 to LUMO. Higher energy, lower energy, it is best that we work out. This is minus 0.618, this is 1. So, what is it? 1.618. So, degenerate transition. So, what we see is that we expect a degenerate transition, a pair of degenerate transitions for HOMO to LUMO plus 1 and HOMO minus 1 to LUMO, right. What is the symmetry of this configuration? A2, AU and B2G. Sorry, B1U and B2G. B1U and B2G, what will it be? It will be B3U once again. So, this is what you expect. You expect one transition, you just work it out from the character table, it will follow. One transition of 1.232 beta and a doubly degenerate transition of 1.618 beta, okay. And the symmetries of transition are AG to B2U and AG to B3U, that is what you expect. Which of these transitions are allowed, which of these transitions are not allowed? I think we know the generic answer to this question. The generic answer to this question is that transitions are allowed when transition moment integral is non-zero. And from the point of view of symmetry, an integral is non-zero when the integrand is, or when the integrand at least contains a totally symmetric part. And if you now think, first of all, that psi I is, what is the wave function from which the upward transitions begin? It is AG, right, totally symmetric anyway. So, we do not even bother about it. We bother about the direct product of psi f and mu. What is the symmetry of psi f? What is the symmetry of mu? Dipole moment. Of course, dipole moment is a vector and it can have x or y or z component. So, what we worry about is what is the symmetry of the direct product of the final wave function and either x or y or z. In our case, what are the final wave functions? What are the symmetries? One is B2u, one is B3u. And what are the symmetries of x or y or z for D2H? X belongs to which symmetry species? To which symmetry species does x belong? B3u. What about y? B2u. What about z? B1u. Okay. So, that is what we worry about. And of course, we know that the component of dipole moment that gives you a non-zero transition moment integral, that determines the polarization of the light absorbed or perhaps or transmitted. We have said that. And then you might remember that when you are talking about a direct product has or a direct product contains the totally symmetric representation only when these two functions of the direct product belong to the same symmetry species. That is a theorem that we had worked out earlier. So, essentially the problem boils down to, does the destination wave function belong to the same symmetry species as x or y or z? If I go one step further, I can say that the transition is going to be allowed if the destination configuration has B1u or B2u or B3u symmetry. If it is B1u, then the transition will be Z polarized. If it is B2u, then it will be Y polarized. If it is B3u, then it will be X polarized. Okay? And we know very well that the destination states are B2u and B3u. These are the two kinds of symmetries. So, now you can answer the question, is again I have written A1G unfortunately, and it took me 4 years to notice it, AG to B2u, is it allowed? It is allowed and Y polarized. AG to B3u, is it allowed? It is allowed and X polarized. Or if you want to write it in terms of this long axis and short axis terminology, then we will say that AG to B3u, this transition, first of all, do not forget our expectation so far is that this AG to B3u is a doubly degenerate higher energy transition. That should be polarized along long axis, X is long axis, right? And AG to B2u, that is the lower energy singly degenerate, well, non-degenerate transition, that should be polarized along the short axis. Okay? This is what you expect. And now, moment of truth, we have to look at actual spectroscopic data and compare. This is your spectroscopic data. You do have 3 transitions, one along short axis, and we assign it to A1G to B2U. You have 2 other transitions polarized along long axis. We assign them to AG to B3U, right. Now, the expectation is that this energy for the short axis polarized transition should be lower than the other 2, and the other 2 should have the same energy. That is the expectation. This is the reality. It is true that the transition that is polarized along short axis has the lowest energy. It is not true, actually, not true. So, what we see is that first of all, you do not have these 2 degenerate transitions. You actually have 3 transitions, and the short axis polarized transition, which you expect it to be the lowest energy transition, is actually a transition of intermediate energy. So, now we are a little confused. Until now we were doing fine, but now we are faced with the question, what happened? where are my degenerate states? Whatever happened to the degenerate states? And the answer is configuration interaction happened. Configuration interaction means you have two configurations which have same energy or nearly same energy, and then they have the same symmetry. In this case, they become talkative configurations. They do not remain by themselves, they talk, they mix, and when they mix, when wave functions mix, you end up getting linear combinations, one of which is lower energy, one of which has higher energy. That is exactly what happens, and extent of this is determined by this interaction integral of psi 1 h psi 2 over all space. That is not equal to 0 if energies are comparable and symmetries are same. So, that is what has happened essentially. So, what has happened is this degenerate pair that you had have formed linear combination mixed, and then due to mixing again you will be able to write a pair of secular equations. Now, you are getting used to this, right, and you will have the secular determinants. Now, you see this secular determinant again when you expand, you are going to get this quadratic equation in E, right. It is going to have two roots. Okay. So, one root will be less than E0, one will be more than E0. So, due to configuration interaction, this kind of splitting takes place. So, we often say no crossing rule, states of same symmetry do not cross each other. Actually, that is something that helps us understand things, but it is actually not right. It is the other way around. There is no question of no crossing, actually they mix, and when they mix they form two states. So, what you see here is not repulsion between states, it is mixing of states which gives you one state of low energy, one state of high energy, right. This is the answer. So, now if I now combine this theory with experiment, what can I do? This short axis polarized transition of 34,700, that has got nothing to do with configuration interaction, right. We know what the expected value of energy of it is in terms of beta, right. What is it? What is that energy? 1.2 or something, 1.236. So, we might as well say that this 34,700 centimeter inverse, that is 1.236 beta minus 1.236 beta, and that gives me an experimentally determined value of beta. There was a question, how do you determine beta? I do not know how to determine it theoretically. There is a way, I do not know so much, but what we have arrived at is how we can determine a value of beta experimentally. Okay. And now, what more can I get from here? I know these values, right, 31,800, 45,200, and I have already determined what is the value of beta for 34,700. I can actually work out this interaction energy and everything. So, by mixing theory and experiment, I can kind of get a good idea, good quantitative idea of the entire scenario. Okay. So, this is what it is. Remember what we got initially, we thought we have got the electronic states, but they are not the final electronic states, they are configurations. And these configurations, if they have the right energy and right symmetry, they can actually interact to give you the final states. That is what has happened here. Okay. That is the end of the story for naphthalene. So, in discussing this, we have learned several things. First of all, we have learned how to solve this complicated, well, organic chemists may not agree that this is complicated, they sometimes handle much bigger molecules, but quantum chemists will agree that this is a complicated problem. So, we have learned how to simplify complicated quantum mechanical problems using symmetry, and in the process we learned also this business of configuration interaction, which tells us that it is not always zeroth order. Very often configurations that you produce can also interact with each other and give you a picture that you do not expect at first glance, right. That is why naphthalene is a good case study. That is it. Thank you.